Today, we are diving deep into one of nature's most mind-bending forces, magnetism. Think about it. It's powerful enough to run entire cities, yet so delicate it can guide a tiny compass needle. And the craziest part? It's completely invisible.
You guessed it, it's magnetism, the silent giant that powers so much of our modern world. And by the time we're done here, you're not just going to know the principles. You're going to understand how it all works.
So, let's do this. We're going to pull back the curtain, moving from the invisible world of forces to the real, tangible tech that they create. Okay, first things first. To even begin to get a handle on magnetism, you have to start with the stage where it all plays out, the magnetic field.
The best way to think of it is like a magnet's own personal bubble. Seriously, it's not just empty space around it. It's a region that's charged up with potential force. So anytime another magnetically sensitive object wanders into this field, bam, it's going to feel a push or a pull. This field, this bubble of influence, that's the real hero of our story today.
So how in the world do you visualize something that's invisible? Well, physicists came up with this brilliant concept called magnetic field lines. And these imaginary lines tell you everything you need to know. Where the lines point, that's the direction of the force. How tightly packed they are tells you how strong the field is. And here's the most important part. These lines always form perfect continuous loops. They have no start and no end, which is a super important clue about how magnetism works.
Okay, so these fields exist. We get that. But where do they actually come from? What creates them? Well, it turns out the entire vast world of magnetism is governed by just two fundamental laws.
And these two laws are absolutely crucial. Think of it like this. Gauss's law tells us what the field is like. It basically confirms what we just saw with those field lines, that they're always closed loops. You can't have an isolated North Pole all by itself without a South Pole attached. It just doesn't happen. Ampere's law, on the other hand, tells us how a field is actually made. And the source is incredibly simple. Moving electric charges. That's it. An electric current running through a wire generates a magnetic field that swirls around it. That's the secret.
And this is where the real magic happens. We've got the fields, we've got the rules that create them. Now we can put it all together to actually make things move.
This really is the million-dollar question, isn't it? We know a current can make a field, but what happens when you take a wire that's already carrying a current and you place it inside another existing magnetic field? Well, something incredible happens. The wire feels a force. And that one simple interaction is the key to pretty much every electric motor on the entire planet. Let's walk through it. It's beautiful. You take a simple loop of wire, right? Run a current through it, and place it inside a magnetic field. Instantly, the field pushes on one side of that loop and pulls on the other. You have these perfectly balanced opposing forces, and what does that create? A twist. A turning force. Physicists call it torque. And that torque is what makes the loop spin. And just like that, you've turned invisible electric and magnetic forces into real, honest-to-goodness mechanical rotation.
So far, we've been talking about fields and currents mostly in empty space. But things get way more interesting when you start putting different materials into those fields. Because, as it turns out, not all matter sees magnetism in the same way.
You can basically sort all materials into three big buckets. First, you have diamagnetic stuff, like water or copper. And get this, they're actually weakly repelled by magnetic fields. Then you have paramagnetic materials, like aluminum, which are weakly attracted. But then you get to the superstars, ferromagnetic materials. We're talking iron, nickel, cobalt. These guys aren't just attracted, they are powerfully attracted. They amplify the field.
So that begs the question, right? Why is iron so special? What is going on inside that makes it thousands of times more magnetic than something like aluminum? Well, the answer is hidden at the microscopic level.
Inside a regular chunk of iron, there are these teeny tiny neighborhoods called Weiss domains. And inside each one of these domains, the magnetic fields of all the individual atoms are already lined up, like a tiny little army, all facing the same way. Now, normally, all these different little armies, these domains, are pointing in random directions, so it all cancels out. But the moment you bring an external magnet nearby, they all snap to attention and align with each other,
All those tiny fields suddenly add up, creating one massive, powerful magnetic response. It's teamwork on a microscopic scale. So, we have the fields, the rules, the motion, and now the materials. Let's put all these puzzle pieces together and see how they build the world around us.
Every single principle we've talked about has a direct, real-world payoff. That force on a current loop that creates torque, that's your electric motor. Ampere's law, saying currents make fields, that's how we build powerful, controllable electromagnets. And those Weiss domains inside iron, when you permanently freeze their alignment, that's how you make the permanent magnets sticking to your fridge. It all connects.
You know, maybe the most beautiful thing of all is that everything we've covered, all the fields, the forces, the rules for electricity and motion, it's all perfectly described in just a handful of elegant mathematical statements called Maxwell's equations. It's this profound reminder that the most complex things we see in the universe often spring from the absolute simplest rules. And it really makes you wonder, doesn't it? What other invisible symphonies are playing out all around us, just waiting for us to learn how to listen?